So tonight we're going to talk about diagnosing faulty electrical parts and other bits of trivia and so on and so forth. So we'll just get on with it. Okay, so we're going to start right out tonight with a poll question number 1. What is the maximum voltage drop allowable across a closed switch? I see it. The voting is getting hot. Go, baby, go. Let's see. Well, so far 22% think it's 2 volts. 16% think it's 0.5 volts. 14% of you guys are jumping on 5 volts. There's a good balance there. 45% of you guys are going 0.2 volts. And the answer is 0.2 volts. That doesn't seem like a lot, but 0.2 volts going through a switch. What is a switch? A switch is not a load, it is a conductor. So if we're going to talk about diagnosing faulty electrical parts, switches are a big part of that deal. Switches probably cause more problems than anything else in the whole business, the whole circuit. They burn out motors, they do all kinds of great stuff, they burn up wires, so on and so forth. But supposedly if I look at this switch, I've got a voltmeter going across it right now, I got 0.2 volts dropping through that switch. What should I have dropping through the switch? I should have nothing dropping through that switch. When I look at that switch with my voltmeter, I should see 0 volts. Okay? Now, here's the result of a voltage drop through a switch. I have a personal relationship with this contactor. As a matter of fact, it freaked me out because I thought I was going to burn out my brand new well pump. This was a brand new contactor. Anyhow, so what we got here is just a good visual. Of course, I pulled the cap off of the contactor. Notice the red. The red color, here's a nice copper color. Yeah, something got hot. What got hot? Well, these points going through here. Bad news. That's something you look for when you're looking for a switch that's bad, if you can see it. But you really don't have to see it. Here's some more photographs. This switch on the left, bad contacts create heat. Well, you can see the charred remains of the Bakelite enclosure behind it. These points are totally fried. And here's the exact same relay, but these points look brand new. They haven't been damaged at all. What's the issue with a bad switch? Bad switch creates resistance in the circuit. A switch is not designed to be a resistance in the circuit. It's designed to be a conductor in the circuit. And so as you're looking for equipment that, well, you're just out there doing your job, you've got some questions about why something's happening, maybe you're replacing a motor because it burned up for some reason, you can't really figure that out. Look at all the switches. Look at all the switches in that circuit, because if you had a bad switch, resistance in the circuit could have easily taken that motor out because it dropped voltage to the motor. What happens when you drop voltage to a motor? Amperage goes up. What happens when amperage goes up? Heat goes up. What happens when heat goes up? You start frying insulation on the motor windings. Bad switches, by the way, are primarily the scourge of inductive loads, or i.e. windings, coils, motors, all those type of inductive loads that you would find in an HVAC system. It's easy to find a bad switch with a voltmeter. That's the way to go. When you're troubleshooting, looking for a bad switch, the voltmeter is absolutely the best way to go. You don't have to open up anything. You don't have to do much at all. Just go across the switch with your voltmeter. And it's, like I say, it's pretty simple, but be careful. That circuit is hot and live. And for you to measure a voltage drop across a switch, the circuit has to be energized. In other words, you have to be measuring across a switch while it's hot. Well, the circuit is hot. Otherwise, if the circuit's not energized, you aren't going to see anything in a bad switch situation. Of course, if the circuit's not energized, it's likely you won't see any voltage either. But yeah, the circuit has to be energized to find out if there's a voltage drop across the switch. The consequences to the circuit load, like a motor, can be disastrous. Now, this is sort of interesting. Inductive loads are the ones that are really critical to voltage drop. If you're working on a resistive load, like an electric element, which is the only thing that really comes to mind in this conversation, I mean, you got two kinds of loads. You got an inductive load, a motor, a relay coil, a contactor coil, whatever, and or you have a resistive load. In the HVAC world, that would generally be a resistance heater, an electric furnace or electric heater or something like that. If you have a bad switch in a resistive load, what's interesting is it's not going to burn up the element, because the element is just going to get less voltage, it's going to put out less heat, and so on. You get a bad switch in an inductive load, like a motor, it's going to start dropping voltage, which is going to cause the amperage to go up, and like I said earlier, then your motor is going to look like that eventually with this nice black insulation inside of it. So this Montana hillbilly says if there ain't no amperage flowing, there ain't nothing happening in the circuit. You have to measure across switches where you have issues or where you're looking for a problem. You have to measure across them while the circuit is energized and the load is operational. Reiterate, a closed switch is nothing more than a conductor, and that's exactly what a switch is about. It's a conductor that can be operated. You can open the conductor or you can close the conductor. It gives you control of the circuit, or gives something control of the circuit. A bad switch drops volts, fries the points, and then continues just to get worse. Now there's somewhat of a myth out there about switches. Oh, we got a bad switch, so I'm going to get my handy dandy little tiny file out and I'm going to tune up those points. Forget it. You'll probably do the project worse than if you would have just left it alone. You cannot file points with anything. When we're talking about line voltage, 120, 240, 440, whatever, if your contacts start to develop a problem, as soon as you file them, you've interrupted the match that has developed over the period of time that contacts have been switching on and off. When you interrupt the match, what's going to happen is the points are just going to fry, the switch points are just going to fry quicker. So bite the bullet, talk to your customer and say, sir, I can't leave the switch in the circuit, I'm going to have to replace it, because if I don't do it now, I'll be back tomorrow or the next week to replace it. If you don't replace it because you see 0.2 volts or more, then you probably will be back tomorrow or the next week or so on and replace it. And then it gets difficult with your customers trying to explain to them why you came back, you didn't do the job the first time, yada, yada, yada. You might have heard that story before from customers. So the problem. Yes, Ricardo, I did say low voltage causes current to go up. Why do you suppose that is? Ricardo's on it. Okay, I'll address that. And I'm just reading Ricardo's talk here. Isn't it that current is directly proportional to voltage? Yes, it is. It is. But when you have a motor turning and you start dropping the voltage, the load on the motor increases because the motor cannot do the work that it was designed to do. So the load on the motor is now not being taken care of because the wattage, i.e. the work of the motor, is not able to meet the demand of the work. So the motor is going to start to get hot. When it starts to get hot, the amperage is going to go up. The more the amperage goes up, the hotter the motor gets. The hotter the motor gets, the amperage goes up. Pretty soon you have a burned out motor. That insulation can only take so much. Does that answer your question? Okay. Again, when you have a bad switch in the circuit, it's not going to act as a conductor, it's going to act as a load. Now, I just grabbed this little schematic out of a previous webinar that we did the other day. Everybody knows what a circuit is, or everybody's supposed to know what a circuit is. Power source, two conductors, and a load. And normally, in HVAC and everywhere else, there's only one load in a circuit. Of course, you can have a parallel circuit that's the big ladder where you have load, load, load all the way down through the ladder. But as we talked about prior, if you've been to any of these dog and pony shows before, each one of those loads is getting the full voltage provided to the circuit, in this case 240 volts. What happens when you have a bad switch, and I just illustrated here as 0.2 volts, what happens is this creates heat. So that bad switch contact now is a resistive load. And you guys all know what resistive loads are. Resistive loads take electrical energy and convert it to heat energy. And as the heat energy increases in that switch contact, the resistance increases. How many of you guys have found contacts welded together? It's not an everyday event, but when you find them, it's sort of ugly because something burned up pretty good if that contact welded together. Okay? Just saying. heat generated by a 0.2 volt drop. You know, I got to confess that I sat here and I tried to do the calculation earlier today on what a 0.2 volt drop would cost. And I took a couple of runs at it. I'm no slouch when it comes to Ohm's law, but I couldn't really get a definitive number on what a 0.2 volt drop would be in a 240 volt circuit. So I just decided I would emphasize what's going on here. As I mentioned earlier, just in the previous slide, here I have two loads in series. I've got a resistive load, the bad switch, and I've got a inductive load, the motor. Okay, so I got two loads in series. That means the motor is not getting full voltage. In this case, it's getting 239. If you guys know your rules of thumb, you'll know that a 240 volt motor with 239 volts applied to it is just fine. It's plus or minus 10% voltage, right? So 239 volts on this motor is going to be just fine. But the real problem is this switch is dropping 0.2 volts now. Do you think it's going to heal itself? Anybody? No? Well, it's not going to heal itself. It's dropping 0.2 volts now. If you would have checked this maybe a year ago, you would have measured across that switch, and it would have been 0, like it should be. No voltage drop, so therefore no heat, no resistance. All right? But over a period of time, the switch has developed enough resistance to consume 0.2 volts of the voltage pressure. Is it going to get to the point where, just as, yeah, light a fire, Jeffrey, that could be. Depends on where that switch is at, what it's mounted on, and so on. But over a period of time, this 0.2 volt resistive switch is not going to heal itself. All that's going to happen is it's just going to get more and more resistive. Maybe, you know, a couple of weeks from now, I come back and measure across that switch. Now it's 0.5, and then a week later it's 0.8. And what happens with that switch as it fails is the failure accelerates, because the hotter it gets, the faster it fails. So that's what I'm saying. When you're on the job, you find a bad switch, 0.2 volts. My personal limit is 0.1 volt. But that's just because I don't like to come back. And as a matter of fact, it's not my switch anyhow. It's the customer's switch, and I want to take care of that customer. I want to make sure that his equipment is running great. So you replace the switch. If the customer doesn't want you to replace the switch, document it on your invoice. Okay? So back to Ohm's law. At the end of the day, what we're looking at is volts and amps, okay? 0.2 volts divided into, let's say, 746 watts, which is, all you guys know your electrical conversions. I know you do. Somebody get on that chat and tell me what 746 watts equals. Okay, Destin, you're Mr. Hot Stuff. Yeah, it equals 1 horsepower. Very good. You guys are on it. Okay. So you can see at the end of the day, the wattage is what causes the heat. It's the wattage. Last week when we did this, I was talking about, it was in the video clip, a circuit breaker is nothing more than a switch. That's all it is. It just happens to be a protection switch. It protects the circuit in two ways. Large overcurrent, it'll trip immediately. A slight overcurrent, it'll trip over time, because it takes time for that heating element, the circuit breaker, to heat up and trip the switch. But at the end of the day, in many cases, a circuit breaker can also become a bad switch. So if you have this mystery trips or intermittent circuit breaker trips or those kind of issues happening to you, and all the years that I ran service and still take care of all my electrical here on the ranch, they happen occasionally. A circuit breaker will start dropping voltage through it, and boom, it's time to change that breaker, because eventually it's going to start doing a nuisance trip thing, etc. Okay, is there a rule of thumb or max temperature on a circuit breaker using an infrared? No, Tim, I don't know what a rule of thumb would be. What I would, when I'm talking about voltage drop, the rule of thumb is 0.2 volts. As far as temperature goes, I'm not sure. I don't know what that number is. All right. Okay, Jimmy. Glad you're new to this because you're here learning. Good for you. So just want to emphasize, a circuit breaker is a switch. A circuit breaker can develop a voltage drop internal to the circuit breaker. And my demonstration in the webinar 2 weeks ago was just take the back of your hand and run down those circuit breaker in the panel. And when you find a warm one, my next recommendation would be to measure across that circuit breaker from power in to power out and see if you got a voltage drop. If you got a voltage drop, you can probably expect it's a circuit breaker. If you pull the circuit breaker out, if you're allowed to do that, I'm not saying that you are, but if you're allowed to do that, I won't be surprised if you find that the clip that goes on the bus bar inside the panel, don't be surprised if that clip is turned brown, all right? Because it's been heating. Heat causes conductors to turn colors, okay? Now, all right, so we're sort of through a lot of switches. I just threw in here checking a current relay. You guys know how to check current relays? You guys work with current relays? If you're working, well, residential refrigeration anymore, they don't even use current relays as far as I know. They're all solid state kind of things. If you're working small commercial, like reach-ins, yeah, just small commercial stuff, up to a half horsepower. In small commercial, you're likely to find a current relay with a start capacitor and an overload. Those small compressors are generally capacitor start. They need that bump to get them going. That's what a start capacitor does. Gives them that shot because they need to start under a load. If you don't know how to check a current relay, it's pretty simple. You see the top footer, well, you can see the current relay here in the start package that came off the side of a compressor. You have the two pins, start and run, or it might be S and M, start and main meaning run winding. You have two pinholes in the side of that relay that slips on the pins on the compressor, the electrical connections on the compressor for start and run winding, right? So when you have the relay right side up, which is the top picture, and I've got it selected to ohms, you've got my VOM selected to ohms, and you have it right side up the way it would mount on the side of the compressor, you should have no continuity, okay? If you turn it over upside down like the lower picture, notice where the pins are, then you should have continuity. Basically, I do 0.004. I mean, that's basically full continuity. There's no resistance to that connection. Current relays are not spring-loaded. They are gravity relays. So all you have to do to check a relay to see if it's there, see if it's working, current relay anyhow, pull it off the side of the compressor, insert your ohmmeter probes, have it hold it right side up. You should have no continuity, turn it over, and you actually, when you turn it over, you'll have the points fall together. And then you should have, like it shows here in the picture, we'll have continuity. Terry, what about measuring resistance across a de-energized switch? Are you sure? De-energized switch, the loaded question for that, Terry, is it a normally closed or a normally open switch? But we can go there in a bit. Ricardo, you said to replace a circuit breaker, should it be with higher capacity if the equivalent is not available? You're asking for trouble. Are you asking me if I should replace a 20 amp circuit breaker with a 30 amp circuit breaker? I wouldn't say that's a good idea. I'd say go down to Home Depot and get the right one. What is a circuit breaker? A circuit breaker is there to protect the wire. It's not there to protect the load. And unless you know what the amperage capacity of the wire circuit is, that could be a problem. Could be a problem. So, yeah, go to Home Depot. Get the right one. Sorry. Okay, poll question number 2. This is a trick question. You guys always like trick questions. I like giving them too. What is the background being used in the presentation photos? The voting is fast and furious. We had 30% voted, 40% voted. Yes, 67% said psychometric chart. Very good. Very good. Good job. Like I said, it's a trick question. Just seeing how many of you guys are familiar with the psychometric chart, because that's going to be the topic of another session, I think next week, as a matter of fact. Right, Brian? Oh, sure. Ian, you took a shot in the dark. Did you get it right? All right, whatever. Yeah, you guys are sort of brutal. Dan, 35% didn't know what you're talking about. Well, that's okay. It's part of my job to make sure they do. All right, so now we're going to go on to capacitors. The deal said troubleshooting or identifying bad electrical components. Well, capacitors are pretty common bad electrical component. Although I got to say, in my 40 years of working at HVACR, not that I really worked, but capacitors are very reliable, a reliable device. But at the end of the day, they will screw you up if you don't know how to check them out, how to replace them, how to troubleshoot a capacitor. It's not really that hard, but you got to know what's going on with a capacitor. If you get the wrong one, or if you don't know how to check it and it's shorted out or whatever, you could be screwed up, or you could screw up your customer's system. Okay, so the number one tattletale, if it happens, and there's no guarantee that this will happen with a bad capacitor, but as you can see on the screen here, I hope, you see this capacitor is sort of swelled up at the top. This one here is sort of a bad photo. It would be better if we would have got it more off to the side, but that one as well is swelled up on the top. So both these images show a dual run capacitor. Anytime you're in a run capacitor mode, although I believe they're getting tricky and starting to get dry ones, but generally speaking, run capacitors are filled with oil. Oil acts as a coolant. It transfers the heat from the capacitor windings inside to the outside of the can, which is what you call the container that the capacitor is in. Looks like a can of tuna fish, actually. But anyhow, it transfers that heat from the capacitor plates, I shouldn't say windings, capacitor plates, to the inside of the can, the metal jacket, and then the metal jacket transfers the heat away to the ambient air. So look for a bulge. All right, if you know what a capacitor should look like and you see a fat one, you better check it out. And that's an easy visual, real easy visual. When you've got a panel open, just glance around, check the capacitors. Are they puffed up? What's happening? The other thing is look for oil on the capacitor can or below it. I don't know what this guy's doing. He's draining a capacitor, it appears. But like I mentioned before, run capacitors, now I didn't say start capacitors, I said run capacitors. Capacitors that are in a metal jacket are typically filled with oil. Okay? So, one, you said, why do capacitors still work even when they have oil all over? It might not be oil from the capacitor, it might be oil from somewhere else. But let's poke in here a ways and talk about it some more. First thing we're going to talk about is a start capacitor. A start capacitor is a dry capacitor. It's not oil filled. A start capacitor is in the circuit momentarily just to start the compressor, generally speaking. You won't find start compressors generally you won't find them on fan motors or anything like that. For you guys that might have a table saw or something, that type of tool, or an air compressor at home, oftentimes they have that bulge on the side of the motor. If you pull the cover off that bulge on the side of the motor, there's a cover plate, it's a little half round thing. You pull that cover off the side of the motor, you'll find there's a start capacitor underneath there. Start capacitors are used to start motors that are typically under a load when they start, like an air compressor, like a commercial refrigeration unit that hasn't equalized, and so on. But start capacitors are dry. How to identify a bad start capacitor? Well, one of the things to look, this visual on the right, it says start capacitor blow plug. Any start capacitor is, well, generally speaking, start capacitors are in a Bakelite black plastic jacket or can, and you will look at the top of that start capacitor, you'll see this little hole, and it's filled with like a clay kind of material. That's what it's filled with. Easy reference is to look at that vent hole, is what it is. I prefer to vent the capacitor than have it blow up like a stick of dynamite. And if the vent hole is open, it's all over, bad capacitor. Do not use that capacitor. The other thing I wanted to point out, and I didn't get a photograph of it, but you see this grippy ring. This ring is holding the top of the capacitor down inside the tube there. Many times when I found bad start capacitors, what you'll see is this top has gone down a little ways, maybe a quarter inch or so, and what you'll see is this grip ring has slid down with it. Sort of an interesting thing. And generally speaking, you'll also notice that this vent hole is open. It's blown out. Okay? All right. So, when you're checking out a capacitor, either a start or a run capacitor, use a capacitance feature of your volt-ohm meter. Fantastic deal. Back in the day, which I can say now, there was no such thing. I remember buying a capacitor checker, and that sucker cost me like 250 bucks. You know, if you don't have the toys, you can't play kind of a guy. That's who I am. So I went out and got myself a capacitor checker for 250 bucks and used that, and I was ever so happy that, you know, like 20 years later, the BOM manufacturers started including capacitance checkers in the digital meters. That was wonderful. It was a great deal. When you're measuring an in-service capacitor capacitance, there's some things to know. As far as the microfarads ratings go, it's plus or minus 10%. Plus or minus 10% is cool and okay. When replacing a capacitor, this applies. All right? So just as a rule of thumb or a point of discussion, if you have a 10 microfarad capacitor, plus 10% would be 11, minus 10% would be 9. So you have a range of 9 to 11 microfarads that would work for that capacitor. Okay? Yeah, on the left-hand side we have a naked run capacitor exposed. Don't look. This could be X-rated. So, going into capacitors, we got poll question 3. Can you change a 120 volt capacitor with a 440 volt capacitor if the microfarads are the same? Oh man, this is neck and neck. Connect, connect. Uh-oh. The no's are winning. There goes the no's. Yep, the S's are, yep, the no's. This is sort of like watching one of those races on the computer, you know. He's got these two bars and they're going along. 73% voted, and then everybody else dogged out. That means 27% of the students out there are sleeping. They've got their computer on, but they're watching TV. They come over and jiggle their mouse every once in a while to pretend like somebody's watching. I know how it works. As a matter of fact, yes. 57% said no, 43% yes. Yes, you can. Ooh, that sounds like a campaign slogan. I can't go there. But yes, you can. What you can't do in changing the capacitor is you cannot go down. If you have, for instance, this capacitor, the image on the left there, this capacitor image says this is a 6 UF, meaning microfarad, and it's a 370 volt capacitor. All right. If I didn't have a 370 volt capacitor and I had a 440 volt capacitor, a 600 volt capacitor, whatever, I could change that all day long as the microfarad rating was within plus or minus 10%. Okay? I can change that with a higher voltage capacitor. What I cannot do is change it with a lower voltage capacitor. I could have a 6 microfarad 220 volt capacitor and I'd be asking for trouble. I'd be asking for trouble. So, no, on the voltage you can go up, but you can't go below. And there's a good reason for that. Let's see if we can figure that out. Okay, I had a little fun over the week and I got to tear things up again, and I don't know how many times I've got a can opener and opened up a capacitor just to look at them, show them to students, and so on. They're sort of interesting. They're pretty simple. As you can see, this is a run capacitor. In that run capacitor, you have 2 foil plates that store the electrons. Those are the electron plates, and they're either charged or not charged, depending on the polarity of the sine wave at that particular moment in second in time. And between the 2 foil plates, there's a very thin membrane called a dielectric insulation. Now that dielectric, the 2 plates, the dielectric's in between them. It's sort of like a sandwich situation. The dielectric is a very, very high quality insulation material, and it keeps those plates electrically separate. All right. A capacitor with a failed dielectric will show continuity or resistance reading between the 2 connection points at the top of the capacitor, the 2 connection points. If you have any continuity from an ohm meter's reading between those 2 terminals where you wire the capacitor, it's a dead capacitor. The dielectric failed because now I have leakage between the plates. If I apply a 220 volt capacitor that you replace into the place where a 370 volt capacitor was, a 370 volt capacitor was specified, but you didn't have one, you had a 220, you're asking for trouble because now that 220 volt capacitor, remember, voltage is pressure, electrical pressure. Now I have a 220 volt capacitor in a 370 volt application, which means probably pretty much that 370 volts is going to be there at some point, and the electrons are going to start making pinholes or electron size holes, which are very small, through that dielectric, and you're going to short out the plates. Okay? And it's going to fail. So With voltage, you can always go up, but you cannot go below the specified. You can't do it. Okay? Capacitor has continuity of resistance reading from the wire terminal points to the can, to the metal can. It's a bad capacitor. It's grounded out. Usually when they ground out like that, they fail in a pretty dramatic way. That's when you're going to find the oil or the bulge in the can and so on. Relationship of the size of the capacitor and how the size of the plates determines how many microfarads the capacitor can store. That's trivia information, but there's a 6 microfarad capacitor laying on the floor of my studio, and let me tell you, there's a lot of stuff there. They wrap it in there very tightly. You can see here, it's just a big roll. I don't advise using it for toilet paper. More training in this series. Is that it, Brian? Are we done? Did we get to it? Holy mackerel. If you get me talking, I can't stop. What you got? Anybody got a question? Okay. Juan does. Checking a capacitor has a resistor. The resistor. Oh, yeah, you know what? I forgot to throw that in there. What should be here? This is a start capacitor. What should be there? A? Yeah, there you go. Bleed resistor. A bleed resistor. And I apologize, guys. I have a photograph. I was going to plug it in. I got spaced out. Didn't do it. Anyhow, I should have a bleed resistor there to discharge that capacitor when it's not in the circuit. Remember earlier I talked about start capacitor. It's only in the circuit momentarily. It's just there as the instant of starting, and then from that point on it's out because the relay opens and takes it out of the circuit. There's a bleed resistor that should be there, 2 watt, 10,000 ohm, that will dissipate the charge that's in the capacitor. If you're handling start capacitors and you don't have a bleed resistor on it when you take it out of the circuit, watch yourself. Because well, of course, the start capacitors are much higher microfarad rating, anywhere from 100 to 400, 500, 600 microfarads. That could smart a little bit if you got your little fingers across those terminals and it was charged. So, yes, it should have a bleed resistor in it. And the bleed resistor will keep you safe, but it will also keep the relay points from getting beat up so bad. Questions? Can I use a screwdriver? Ricardo. Oh, who was that? Yeah, it was Ricardo. Can I use a screwdriver? It's better than your tongue. That's all I'll say about that. You're welcome, Terry. Yes, you have to. Remember, Scott, you have to, if you're going to use a meter, you need to isolate the circuit. Generally speaking, of course, you're using a voltmeter, you're looking for voltage, that kind of thing, but ohm meter, capacitance meter, yeah, you got to isolate it. Isolate the component out of the circuit. Do I like the adjustable types of capacitors, you mean? I think that's what you're talking about. Yeah, they do the job. Whatever's in your toolbox. I'm trying to, Supco, I believe, is the company that makes those. How did you check the dual cap back in the day? Well, you got the common terminal, and then you also have, one goes to usually the fan motor, the other one goes to the compressor. You just check them the same way you do any capacitor. You go from common to the terminal, like the 10 microfarad for the compressor, and from common to the 3 microfarad for the fan motor. Yeah, it's the same thing. Same thing, it's just now you got 2 in 1, and it has a common terminal that serves both capacitors. 3-phase motors don't use start capacitors. No, they don't. They don't need them. They got more than a juice to get going. Have I been fishing today? No, I haven't. As a matter of fact, it is still winter in northwestern Montana. We got another 2 or 3 inches today. I am so tired of winter. We've got about 2.5, 3 feet of snow on the ground. I'm thinking about heading south. Yeah, Scott, come on up. You can start shoveling. What about riding a horse? No, this cowboy doesn't ride horses. The only horses I ride are the ones you can put gas in. What's a BFL? I'm afraid to ask. No drinking. You've got rain. Going fishing Baja. Oh, bite me, Raul. Bite me, Raul. I don't want to hear it. Baja. It's warm. The water's warm. No. 85 today in SoCal. I know. I come down there. Come down and file. Golf in Ohio. Give me a break. Tyler? No way. You're welcome, Christopher. We're winding down. Let's see. Jimmy, sorry, it's 750 volts or watts, it equals 1 horsepower. It's 746 watts equals 1 horsepower. Okay? It's about 3.1 amps at 240 volts. If you know Ohm's law, you can do the math for 120 volt. And by the way, those energy conversions are a real good thing to keep in your noggin, and then exercising once in a while. Should I replace the capacitor if I remove the bleed resistor? Jeff, number one, you shouldn't remove the bleed resistor unless you're replacing the capacitor. And in a lot of cases, there's nothing wrong with the bleed resistor. You can take your ohm meter and measure it. It should be 10,000 ohms. And then in many cases, you just put the bleed resistor back on the new capacitor. Livingston where, Lloyd? Oh, Lloyd, Livingston, Montana. Good for you. Oh, Raul, motor control seminars. Actually, what you guys can expect is this boy's going to start teaching live at least once a week, probably twice a week. The studio is pretty much ready. We're just going to run a live class twice a week. You can probably expect to see that happen sometime in April. In Kentucky, Jimmy, good for you. I like Kentucky. Hey, Art, we do some live classes in California, down in SoCal. They're usually fairly specialized in nature. Yeah, Ricardo, poor baby, 60 degrees. Come up here. I think it's about 25 right now, and it's snowing hard. Heck yeah, Raul, send me a picture of that swordfish. I want to see it. I got the best well that you can imagine, Paul. 195 feet, 60 feet of static head, and 45 gallons per minute as a pump test. Yeah, when you live on a ranch in the middle of nowhere, Montana, Paul, you end up being all the utilities together. It's being the sewer district I don't like. Good night, Terry. Carry on, Harry. Glad to see somebody from Florida. Good for you. Yeah, why you should know air? What do you mean, why should I know air? Mark, air is our business. You should know everything about air, everything inside out and backwards. Thanks, Philip. Good night, see ya. Very right, Terry. You took that out of my mouth. Air is the first word in air conditioner. You're right, Ricardo. Without air, we die. As a matter of fact, atmospheric air is 21%, oxygen, 78% nitrogen, 1% rare gases. The human starts to pass out at 16% oxygen. So we're sitting in a 5% zone. Very delicate. All right, guys. I appreciate your attention. Hope you got something good out of it. This is Compton signing off. Yes, we are Rex. We are the best of all trades. See you guys later.